integrating f prime divided by w minus z squared. In other words, you can use the Cauchy generalized integral formula for calculated derivatives by integrating.
Well, so you wouldn't even need, so what you're saying with the Cauchy general, you don't even need to have the original formula, or you don't have to have the original, like, big F. All you would have to have is any, like, as long as you have as long as it's a continuous derivative or of a function before it, you can always find anything after it. Is that what you're saying?
Yeah, I'm saying that there's no, like, just once complex differential function.
Okay.
If it's once complex differentiable, it's automatically twice complex differentiable and so forth on down the line.
Okay, so there's never a point where, okay.
And that ultimately rests on Cauchy's integral formula. And it kind of, notice, I mean, you might worry that the w minus z is singular, like so that integral wouldn't exist. But the thing is, w is taken from the boundary of d, z is in the interior. They're not equal, and this is complex. So w minus z is non-zero, means it's something you can divide by, because complex numbers are a field.
Yeah.
In an algebra, if you just kind of like fuzzy dive ahead, that would be more troublesome, because if you have just a difference of algebra elements, it could be a zero divisor. Maybe you have no business dividing by that.
Yeah.
So that's sort of one concern that you could think about. It's
Yeah.
like a stumbling block for making sense.
Yeah, I could see it in the null numbers where you could pop out a zero divisor.
But getting back to complex again, if you have the function with, see what's the conditions here? Continuous f prime z, right? Then you can calculate f prime prime by just integrating f like that. That integral exists, and so forth and so on. So you can calculate as many complex derivatives as you want. That is in stark contrast to theory of real functions. Do you know an example of a function which is like once differentiable but not twice real differentiable? I'll start out with G.
Zero. I'm thinking of something you divide by, and if you square it, it gives you zero.
How about this? Now that's a function which is continuous, but not differentiable at zero.
Yeah.
Everywhere else is fine, right? If you look at x times absolute value of x, this thing, what it is it's minus x squared for x less than or equal to 0, and it's x squared for x greater than or equal to 0. You can put in, so it's graphically like a quadratic married with another quadratic like that. No, it's not a cubic.
Yeah. This first thing I was like, huh?
So what's G prime? Well, G prime.
Okay, yeah.
And that's fine. It exists because those derivatives.
Would it?
Yeah, I mean it's this. That's G prime, you know.
Yeah. Okay. Yeah.
Now, G prime prime. Now that's the one that
No, you couldn't get it.
yeah, we get. You know, this is G prime prime. The derivative does not exist at 0. So this is my go-to example of a function which is once but not twice differentiable.
Yeah, you get that.
Yeah, if I understand correctly, this example goes back to like piano. I mean, who knows? Maybe more than. I mean, it's such a natural example. I'm sure lots of people have it, but there are papers on this function and it's higher. Like you can continue this game and do like
X squared.
yeah, x squared or x to the n.
Yeah.
And this thing will be
Differential n minus 1 times.
n times, I think. This is once differentiable, but not twice. This is n times differentiable, but not n plus 1
yeah.
time. So, yeah. But the point is, there are things like this in the theory of real calculus. So, if I was to look at, say, for example, the algebra r cross r, right? Then I could look at, you know, f of xy equal to something like, I don't know, x value of x, you know, y squared x value of y. That's a legit r cross r differentiable function.
But they'd be differentiable. They wouldn't be the same amount of differentials.
Yeah, it's just once differentiable.
Yeah.
Because even though this is twice differentiable, the fact that that fails to be differentiable after the first time, this is just a once differentiable direct product differentiable function. So I know as I start to go into the theory of integral A calculus, I cannot hope for the riches which are present in
Yeah.
complex theory. Because complex theories have this beautiful once differentiable,
Always.
differentiable. And in fact, now you gotta be careful. I do have a theorem in A calculus. I have this theorem, right? If f from A to A is smooth in the real sense, and once A differentiable, then f is A smooth. But that is based on an assumption that f is smooth in the real sense. That is not true for like the example I have right above the theorem.
So like it's smooth in all the real like what if you don't have components that are real? Like what if you're like mapping from like
How is that? Why is that true? Yeah. So let's look at. All right. So we know. Let's for the sake of f is a differentiable, right? So what we know is that f prime of p is equal to dpf of 1, right?
Yep.
And of course, you know, dpf is in the right A differential function, right? So we also know that f prime prime. Sorry, try to. Ooh. So real smooth. All right, so the question is, what about f prime? If we let g equal to f prime, right? Does, you know, does dg is dg at the point p an element of Ra, right? That's what we need for it to be, for the derivative to be a differentiable. Okay, so what's that? How can we judge that? Well,
wait, if g is equal to f prime, well we know dpf is but f
I can make the proof a little bit more concrete and assume that we have a basis which begins with 1 if you'd like.
No, I'm thinking about whether, so if you take a smooth function, isn't there something that says if you have a smooth function from an algebra to an algebra that the derivative will also be smooth?
Yeah, I'm trying to explain right now why it is that if we just assume that the function from A to A is smooth in the real sense, meaning that all that really means is that the partial derivatives of all order exist and are continuous. And then that coupled with the assumption of A differentiability, which is right A linearity of the differential, well, that implies that F is A smooth, which means that the differentials of the derivatives, F prime and so forth, are also right A linear. So like, why is it that we can, you know, dg of, you know, how's it go, v star w or whatever. What is that?
dg of b star w.
Oh, that's what we'd like to, I mean, why is that true?
Oh.
See, this is df prime of v star w. I don't know if that helps or not.
And, what is the name for that? Or are we saying that doesn't hold the,
I think that my current notation is not helpful. Like, let me try to, I'm gonna dial it back here
okay.
and try to give this proof to you in, using partial derivative notation. I think we'll have better luck there. So we assume that partial f partial x j is partial f partial x1 times vj, right? Let's suppose, you know, 1 v2 da 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 vn basis for A. So these are the A Cauchy-Riemann equations, right? I think we'll do better there. Because to make sense of the argument I was just going through, we have to have more familiarity with like iterated differentials.
This
Which
is
is
what
not
I
a
was,
happy place for you at the moment, or me.
this is what I was talking about. From that, can we not assume that a dpf of v star w is equal to a dpf v star w? For all v and w in the algebra?
So what we'd like to see is that the Cauchy-Riemann equations are also true for the derivative, right?
Yes.
But what is the derivative?
In the most basic sense, wouldn't it just be the quotient thing?
Yeah, let's see. Well, but we don't want to do that. But I mean, f prime was dpf 1, right?
Yes.
Which is also partial f partial x1, right?
Yes.
So really, this is partial xj of partial f partial x1, right?
Mm-hmm.
Now, so like fundamental criticism, hold on a second, how can I do that? Like, why am I allowed to take the jth derivative here? I've assumed that the function is smooth in the real sense, right? That means partial derivatives exist. That's why that's okay. And now what?
Oh, we can rewrite, right?
There you go. And we can switch the order, right?
Mm-hmm.
That's really partial x1 of partial f partial xj, right?
Yep.
These commutating partials, and then I can use the Cauchy-Riemann equations here. Right. and then I have, you know, partial squared, well I have partial, I mean yeah I can write partial squared, but what I have is I have partial x1 of partial x1, but I guess I should really just write that as f prime, right? So this is partial f prime and partial x1 times Vj. So, I mean, what's that? Well, oh, that's me, isn't it? I'm gonna get somebody. Bing, 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 bing. Well, UWA president, what old fancy pants was this about? Oh, Memorial Day's thing. What do you know?
Par. Oh, okay. Yep. Nice to know.
So this equal to that. That is the needed A Cauchy-Riemann equations for f prime.
Yep.
So thus, df prime of v star w equals df of v, df prime of v star w, right? I mean, it's just easier to sort through it in the partial differential notation, honestly. Like, it's just a happier place. So, therefore, f prime is a differentiable.
Oh yeah, because you can rewrite it the same way with those new Cauchy-Riemanns.
So just to say, you know, where this is going, generally, if you had the jth derivative of f, well, that's going to be partial the jth derivative of f with respect to x1, you know.
Is that partial j of f?
That's what it's supposed to be.
X.
So what I'll really try.
Wait, so if you have the jth derivative, we would write that as a df of jb.
I mean, I could also write this d to the jf,
Yeah.
d zeta to the j, I guess. Like f prime prime. Sad zeta. I mean, to complete the proof, like assume this is true for j, and then you assume that this formula holds, and that f prime, the jth derivative is a differentiable, then you can prove that j plus 1th derivative is also defined by the j plus 1th derivative of f with respect to x1, and it is also a differentiable using induction. But it's really just this, basically this calculation still goes through if you replace that with like as many primes as you want.
Yeah.
That just puts as many derivatives with respect to x1 as you want here, and you flip the jth derivative outside to the inside derivative, use the Cauchy-Riemann equations on the
New one, yeah.
or something like that. But the key assumption here in this theorem is that it's smooth in the real sense. So that is not something that had to be assumed in the complex analysis. Like the preamble here to the Cauchy's generalized integral formula is just that it's holomorphic and continuous f prime. That's not an assumption about higher real. There's no assumption about higher real derivatives. Although it is true that if it's like if you, instead of thinking of it as a complex function, think of it as a real function, then it is real smooth as well. Because complex smooth implies real smooth. So yeah, Now, let me see if I can finally get back to the point here. So, if we study calculus like over an algebra, then it behaves pretty similarly to, well, what happened?
Nothing.
Nothing.
Mom's going crazy.
No.
But don't worry, your kids will say that about you one day.
I'm sure they're hard to do.
No. Well, maybe the oldest one.
Yes. The oldest two. Alright, so let me just get to the point here. So I've shown you a little bit about complex, right? So if we're in an algebra, right, it has multiplication star, and if you've got a function which goes from the algebra to the algebra again, and if you've got a curve, which is a mapping from some subset of the reals, you know, to the algebra again. So then you can define the integral of f of, I call it f of zeta d zeta. I just start throwing stars into stuff sometimes. I don't think I put a star there. Oh wait, no, did I? Didn't I? Oh, I did. I did put a star there. And, you know, that's just going to be the natural thing, which is the integral over the interval of f of, you know, let's suppose that, you know, c parameterized by gamma. All right, so like f of gamma of t star d gamma dt dt. So, and this is the integral over that interval, you know, so it could be like t0 to t1 or whatever. So same thing we did for complex, all right? And if you like, you could break d zeta into like dx1 plus like v2 dx2 plus vn dxn, where if you know, if v1 is the identity in the algebra. But of course, you know, more generally, if one wasn't the identity, you could look at your d zeta as being like v1 dx1 and so forth. And if you had f equal to like u1 plus v2 u2 vn un, then you could define the integral of f of zeta d zeta times d zeta as sort of like just what you'd expect. So like, you can multiply these out, right? You can multiply these out, and you'd have n real integrals, n real line integrals over the curve, whatever. So every algebra integral is an ensemble of n regular line integrals. Okay. So you have that's the basic setup. Theorem. You have that the norm of f of z is less than or equal to m for z in your curve. And if you have that m sub a is, you know, the norm of z times w is less than or equal to ma, norm z, norm w,
In other words, m sub a is the some multiplicative constant for the algebra, then the norm of the integral over the curve of f of zeta, my zeta has become a z all of a sudden, sorry about that, f of zeta d zeta norm less than or equal to, now we had the ML theorem before, right? Now we get the mammal theorem. So m sub a, big M, and then L, where L is the length of the curve. So the bounding theorem for the integral over an algebra also necessarily involves the submultiplicative constant of the norm. So that's something different. All right. Now, do you have the paper open?
Yeah.
If you look at equation 141
on your original paper.
yeah,
141. Okay.
it's on page 45
Mm-hmm.
or 46, depending which number you're looking at.
Yeah, it's right under theorem 10.4.
So you see there, I calculate the norm of the integral, and there I'm using that Riemann integral, that like Riemann.
Yeah.
Well, not even the integral yet, right? The limit is m goes to infinity, we give you the integral.
Yeah, the z star w. Oh wait, but I thought that one was z minus w, like the modulus of z minus w. If you're using that one, or am I equating two things that
Are
aren't?
you thinking of we had division earlier? That's a different thing. But
Yeah.
this one here, like the sum f of zeta I times delta zeta I, that's the, you know, going back to that definition of, that's the other way we could define the A integral,
Mm-hmm.
all right? Now that is by properties of the norm, triangle inequality less than or equal to the sum of the norms. And then I use the submultiplicative constant to, so you notice I have got norm of the product of f zeta I and delta zeta I.
Mm-hmm.
The next term, I've got the norm of each of those separately times m sub a. That's the definition of m sub a, that we can break norm of a product into a product of the norms times that constant. And that's going to be larger than it. And then,
Look at what's now. Where's this big M come from though?
and then the big M is by assumption, we have a bound on the function of the curve, the norm of the function of the curve,
Okay.
so that's that. And then this remaining thing, sum I equals 1 to m of the norm of delta zeta I, well that's the length of all the little delta zetas that form the curve, so that in the limit becomes arc length. And so there you go, that's the proof of the ML theorem, the mammal theorem. So, and on the next page, I prove in equations like the paragraph there, and equations, maybe proves too strong. I give plausibility arguments. I mean, whether or not that's a proof is in the eye of the beholder, I suppose, but equation 142 and 143 should indicate why we can trade the Riemann sum formulation for the, you know, integral of the parameterization of the curve formulation. Two different integrals. There it is. So I state that as a theorem. So I stated this is the definition, but as you can see, I took the definition to be the Riemann sum in the paper here. And then I derived my definition from that 142 and 143. So, you know, whatever floats your boat, right?
You're talking about theorem 10.5?
Theorem 10.5. I gave that as the definition.
Oh,
Yeah. This, I mean, I was arguing this is the definition here, but the definition in my paper was not that, but this is actually theorem 10.5. I think the definition, oh, where was my definition? Definition 10.3 actually. So I took the Riemann sum as the definition, mostly because it's It's most convenient. The only thing I ever use that for is to prove the mammal theorem. Like, that's the sum total of my interest in that definition. But it is useful for that purpose. And so, hey, here's an example, right?
Yeah.
We're in the hyperbolic numbers, and what are we doing? Oh, I'm not even doing it. I mean, this is kind of a meta example. We've got a function f, right? It's u plus jv. And what's the integral of f d zeta look like? Well, this time it's u dx plus v dy plus j times the integral of v dy plus u dx. So as you can see, the hyperbolic integral, it is a little different than the complex integral, right? The complex integral...
You get that minus out of there, right?
Exactly, you get that minus. I guess the j imaginary part of it is kind of the same. It just flip, like in the complex integral, the second integral, the imaginary part had to do with the integral of like vu, right? And that's still the case for the hyperbolic integral. We're looking at example 10.6. But the real part is quite different, isn't it? Because it's, yeah.
Wait, the real part? I thought the imaginary part had the negative with it.
That's right, but the product of I and I gives you -1, and that fed into the real component of the complex integral.
Yeah, that's right.
So now theorem 10.7 is that chain rule I was saying is so important. So I talked about a chain rule in our previous meeting, but that was a chain rule about a composition of a function of a variable to another function of like it was still about going from like, it was a composition of two algebra differentiable functions. Here I'm mixing flavor choices. Like I've got a differentiable outside function, but I've got a valued real differentiable path as the inside function. So it's the composite of two different things. But there is a natural chain rule, and there it is. So, and the proof is on the next page here.
So the sum of I to the partial f.
I should actually go through this proof.
Okay.
This is one of those things that was not guaranteed. This is one of those things that breaks down for general functions on the algebra. A differentiable functions have a nice chain rule. So let f from a to a be a differentiable, right? And gamma from I to a be real differentiable. So we can look at d dt of f of gamma of t, right? Now, for purposes of, simplest understanding, let's think of A as Rn. All right, so we can fall back on Calc 3 intuition. And everything I'm telling you here straightway adapts to the context of finite dimensional norm linear algebras where we define partial derivatives in a similar fashion. But okay, get that out of my system. So we can think about f as a function of x1, x2, all the way up to xn, right?
Yeah.
So what does the chain rule look like when you have a function of x1 through xn, right? You'd write, well, okay, so this is the sum I equals 1 to n of partial f, partial xi, right? Evaluated at gamma of t times d gamma I dt, right? Where here I'm assuming that gamma is like gamma 1, gamma 2, gamma n, just for the sake of notation. Right, that's what the chain rule looks like for a function of n variables. So at the moment, that's just pretty standard, like calculus 3. Okay, that's not honest. It would be calculus 3 if we taught it as an honors course to just math majors. Okay, right?
So So now that we've got that, what I thought, would we have to multiply by some jth term, some bj?
Oh yeah, devil's in the details here. F is a valued, so these are actually vectors.
Vectors. F is a valued for the vectors.
Okay, so like, oh goodness. I can give you an example, but, all right. Okay, so I'll try to give you a complex example. F of z equal e to the z.
Okay.
So this is actually e to the x cosine y plus I e to the x sine y.
Okay.
So if I look at f of, like t squared plus I t to the 7th, that would be e to the t squared cosine of t to the 7th plus I e to the t squared sine of t to the 7th. So if I differentiate that with respect to d, I get stuff. Two t e to the t squared cosine. I regret this example. Minus e to the t squared sine t to the 7th. We will eventually get to the point here. Plus I 2t e to the t squared sine t to the 7th e to the t squared. I'm missing a times 7t to the 6th here, obviously. 7t to the 6th cosine t to the 7th. Ah. Lovely, there it is. Okay, here's the thing. This, all I really should have written, if I was less of an idiot, is that partial f partial x is what it is, e to the x cosine y plus I e to the x sine y. And partial f partial y is minus e to the x sine y.
Or I cosine.
I e to the x, yeah, cosine y. So, but my larger point is that partial f partial x here is a vector.
Okay.
I mean, it's, if we write it in the other notation, it's this, right? So like in the same sense up here, partial f partial xi is an a vector. It's an n component real vector, it's an a number.
Okay, so going back then.
So it's okay that they're vectors. It's just that this is the chain. So that's why I was saying, made that snide remark about it really it's Calc 3, but it is perhaps the part of Calc 3 that you were never taught also.
So the partial f partial xi to the gamma t. Can we not say that's partial f to the x1 times? No, I'm thinking of something else.
Yes, think that. That is partial f partial x1. Think exactly that. Partial f partial x1 of gamma t, right?
Yeah.
Times vi, right?
Yeah.
And there's a times here that oh wait a minute, no, there's no times there. Sorry. V gamma I. No, this is just real scalar multiplication. This is by the Cauchy-Riemann equations.
Yeah.
A Cauchy-Riemann equations. That is straight up, that is f prime
Yeah.
of gamma of t.
Yeah, it is, because we said that, yeah.
But this also, more importantly, this has no I dependence,
Yeah.
so I can pull it by properties, the way the distributive property of the algebra. I can pull that out. Times over the algebra, right? The sum. I equals 1 to n of, and I can write these in whichever, I mean, you can write the VI second, or I'm going to write this one. I'm going to, scalar multiplication, I can either put on the left or the right, like this is the freedom I allow myself. And whatever, it was fine to leave it the other way. But the point is, when you look at this, what are you looking at?
I'm looking at, oh, this is the summation of partial derivatives on BI,
Right, I mean, what,
or straight up derivatives.
yeah, if I take d gamma dt, I got what? I got d gamma 1 dt, right? So I can also write that like v1 d gamma 1 dt, vn d gamma n dt, or you can put the v's first or last, whatever. The point is, and I hate to erase this example, on the other hand, I don't hate, I mean, I will just say this.
You can get rid of the following.
I will say this, like this, if you tilt your head and squint, you could see it as being f prime of t squared plus I t to the 7th times parentheses 2t plus 7 plus 7i t to the 6th, you know? Now the f prime, in this case, f prime of z is literally the same as f. So like, I mean, just to, before I erase this, because I just want to, since I wrote it all out, you can see this term and this term over here come together to give you this times that. Because it is nothing more than the exponential evaluated at t squared plus I t to the 7th. And when you look at this one and that one put together, it's exactly this times that, you know. But up here, what we have, that's nothing more than just d gamma dt. So what we got, and this is f prime. So f prime of gamma of t times d gamma dt. But don't be deceived. There's quite a bit going on in there. Because that is the full-fledged algebra product. So for an n-dimensional algebra, that's an interesting product. I mean, there's all kinds of quirks and features in there, you know.
We got, how do you get rid of the BI?
Because that's what d gamma dt is. This is,
Oh. This sum is
I mean, these are the components, the ith component, that's the basis vector. You put it together, you just get the derivative. It's the component-wise definition of derivative of a valued function of a real variable.
yeah.
And that, there you go. I mean, that's the chain rule. And that chain rule straight away leads to the fundamental theorem of calculus over, you know,
An algebra.
over an algebra, namely this one, that if we have, you know, the, if f prime of zeta is equal to f of zeta, for zeta in C, which goes from P to Q, right? Then the integral over C of little f of zeta star d zeta is equal to big F of P minus, well, f of Q rather, minus f of P. And the proof is the same as the one I showed you in the complex case.
Yeah, it is.
It's just based on this chain rule we just worked out versus the complex chain rule. And by the way, the complex chain rule is equally mysterious. Like it is very neat. I really don't think enough fanfare is given to that chain rule in the standard complex analysis course. But anyway, so you get that. Two fingers scrolling at me again. Now, and then theorem 10.9, I start to get into some of the more topological features of the A integral. So I'll write them out here. Now, did you do this in Calc 3?
It's connected subloop and a rule. No, it didn't look like it, at least maybe it did. Let's see the feedback.
So if this is true, so you got some like sort of universe of discourse, like U is a connected subset of A, all right? And so number one is that these are equal for all curves that have like, you know, the same terminal points. They could cross each other, it's fine. They can be all kinds of whatever, but. So this is the following are equivalent. Number one. Number two, the integral and this here the C is a loop for all, I mean, so this is for all pairs of paths with the same terminal points, and this is for all loops in U, all right? And then three is that there exists F such that df d zeta equal to F on U. So there exists a antiderivative on the totality of the universe of discussion there. And the proofs that are given in Calculus 3 still work here. So like, to prove 1 implies 2, what you do, suppose 1 is true, all right? Then you take a loop.
Well, couldn't you just get rid of that arbitrary point where C1 and C2 come back together and just say that's part of the function, and since C1, C2, I think that's how I would think about it. So you get, so C1 is a function, C2 is a function, where they curves and or a path, like you could make an arbitrary point on C, right, and say C1, C2, and they're both paths.
Right. So that's essentially it. Is if you have so suppose you have a loop, take your loop, pick another point, not pick 2 points on the loop without the being interval, and then divide the loop into the upper half and the one piece and the other. Then you can you can take the loop and cut it into two pieces like that.
Yep.
And so because, you know, the other, and then it has to do with the orientation, right? Because like the integral along the opposite, the reversal of C2 is minus the integral over C2. So you need that. But that's true for the same reasons it was in Calculus 3, because of the way it's linked to the parameterization of the path. So yeah, that's 1 implies 2. Take the loop, break it into two paths. And then to imply the 2 gets 1. So you take your two paths and make them into a loop. Well, that's a little bit dicey, because if you had two paths, you could have some mathematician do this to you. So I guess technically you gotta like think about lots of loops, but you could put them together and do the analysis to prove you get 0, 0, 0, 0, 0, 0, 0.
Yeah,
And
well,
so-
can you just say like every time it crosses, you could just do each loop as like one loop?
Right. I mean, every one of these loops is 0 by
Yeah.
assumption of 2 implies 1.
Mm-hmm.
And then because they're all 0, that means that this integral is equal to that integral, this integral is equal to that integral, this integral to that integral, this one's that one, this one's that one, this one's that one.
Yeah.
And then you rearrange them, put them all together, and you got 1. Usually I just, when I'm teaching Calc 3, I don't even think about intersecting curves. I just go, well, if you have two curves, then it's a loop. So you can, it's essentially the same argument, 2 implies 1. And then 3 implies 2 is easy by the fundamental theorem of calculus, because if you just take a loop and, you know, it goes from P equals to Q, you know. So if I assume this is true, that means that there exists an antiderivative. I apply the fundamental theorem of calculus, I get f of p minus f of, or f of q minus f of q, which is 0.
Yeah, because
Bam.
they're the same point.
Now, this implies that
Oh,
is not as easy.
so you're saying that you have an integral that equals to 0. And how would that say that you have that f? So, well, little f is equal to f prime, right?
Right, so it turns out, so like I just explained to you, 1 if and only if 2.
Yeah.
Right. It's, for whatever reasons, I find proving this implies that is the easier path. And so the essential proof of that, because if I can get this implies that, we're done. Because it's also easy to see that, I mean, 3 implies 2 and 3 implies 1 are easy. Three implies 1, you know, this is P, this is Q. So it's f of Q minus f of P for both. They're equal. 3 implies 1. 1 implies 3. It's actually a little bit sneakier. And basically it comes down to this. Define f of zeta equal to the integral from pick a point in your domain of discourse, and integrate from zeta naught to zeta f star, oh, I'm using eta now. All of a sudden I got an eta in here. Oh, it's because I'm using, oh, I guess it's because I see. It's because I'm worried about like double, I'm really not confusing variables.
Wait, can't you just say that 3, if you have a statement 3, you will always be,
Oh yeah, given 3 I can get 1 or 2.
yeah.
But how do I construct, there exists f, big F. How do I construct the antiderivative?
A big F or a
of
little
f?
f such that df. Wait, so say that one more time. How do you construct f?
Like 3 is there exists an antiderivative of little f. Okay, assume 1 or 2 is true.
If you assume, say f is differentiable.
Little.
You're saying there exists an f such that there's an antiderivative on little f. Just say f is differentiable once.
But I'm not saying such a thing. I'm just assuming that f is a function which has property 1 or 2. I mean, I'm going to go with property 1. F is.
I thought we were trying to go from 3 to.
I may be assuming f is a differentiable here, actually. Now that I remember.
If you do assume that
Little f is a differentiable, I think, is my assumption. You know, I don't really say what little f. I just say little f is a function. And following our equivalent. I do think I need to know that little f is a differentiable here. Otherwise,
yeah, but
something breaks down here.
I'm just saying the premise of 3 is you start with 3, so you're saying there's an
No, we don't start with 3.
Oh,
We're trying to prove 1 implies 3.
Oh.
That's what we're left with here. We've already said one if and only if 2, and 3 implies 1, and 3 implies 2. Again, it's easy from FTC.
Okay, so
What is not obvious is that 1 implies 3. So 1 implies 3. What I get to assume is path independence. Right? And then I need to somehow construct the antiderivative. Notice that this notation right here is like a little sketchy, right? Like, we didn't even define it yet. Well, by this I mean, this notation is good given this condition. Because it doesn't matter which path we take from z naught to zeta. I mean, from zeta naught to zeta, they're all equal, right? So I can just, this is single valued. By assumption of 1, this is single valued. Here, I'll give you a second, I'll be right back.
okay. I just like
Yeah, I know.
I haven't I gotta prove that there is a big F that's differentiable. If you say all component can I not assume? I'm going kind of wild, but we have 1, and we're saying that 1 implies 2, and 2 implies 1. So can we say that